Hello, everyone. Welcome to the first lecture in the series of OFM 2026 preparation for the physical Olympiads. I'm Zizi. I have been to IFO like twice, luckily, and I hope you guys can do the same too. So, today we're going to be talking, like, the theme of today is thinking like a physicist, thinking like a physicist. So, essentially talking about like the tools that you need, and like the mental models that you have to have. So yeah, stuff like what like when a physicist encounters a problem, like in what dimensions do they start thinking on? Like do they start like just jumping right into like the math, or do they like think from a higher level? And the answer is going to be a combination of both. So yeah, like without further ado, let's just get started away. And like I think I speak well, I guess I don't think I speak for all physicists, but I think I speak for most physicists when they say like the first thing that they do is to look at if the equations make sense. So what does that mean? So if an equation makes sense, that means that the units have to match up, which is like something that we keep iterating every year. But like people like because as a high school student, you don't get that kind of rigorous training that like, oh, okay, I just read down this equation and maybe yeah, I'll get marks. Um, because I followed the expected um paths. I followed the expected working, so like this result should be correct. But how do you know it's correct if you don't know the expected workings? So as like if you do a general problem out there, you don't know if you're doing it right or not. How do you know you're doing right? Well, the first time we check is units. So this is really useful. When you're like deep into differential equations, when you're deep into a whole whiteboard of math or whole like blackboard of math, how do you know like when you've made a mistake? So units. So which is something that physicists like to give a name to. It's called dimensional analysis. So what does dimensional mean? So this dimension here doesn't mean it's like the one dimension, two dimension, three dimension. Well, it's kind of like that. The reason why it's called dimensional analysis is because we call units dimensions. So if you have so what are some common units? So for example, length has dimensions of meters, um, units of weight. Sorry, not weight, mass. Common mistake. Mass and weight are not the same thing. So units of mass is kilograms. Units of time is seconds. Um, and yeah, there's a whole list. So let me just like kind of list down like what else we have as the base SI units. So oh wait, yeah, sorry, a little bit of history. So back in the day, when people were doing trading and stuff, they were like, I don't know how to standardize stuff. And then like afterwards, like people just like kind of use their own convention. And then afterwards, um afterwards some began to be done. But the thing is, like, when science is being done, like, we were still using, like, the back in the day, like, trading methods. So, like, there wasn't really one standardized unit system. And then the French people were like, you know what? For the people, we have to make, um, like a community standard. So, like, it's like SI units. So, yeah, so, like, it's French because, it's a standardization thing. Like, the upper class people cannot, like, like sell us more stuff than we bought because we use the same units. Because it was quite a genius scam actually. Like if you want to sell like someone a piece of cloth, you say that, oh, this piece of cloth is actually 100 meters. You don't know because like you use a different system than I do. Because I use a system where this is 100 meters, you have to give me $10,000, which is like crazy. So yeah. Anyways, so what else is there? There's electric current. So I'm just gonna list down the SI units. So there's current, which is amperes. Hopefully you've seen these things before. There's temperature, which has units of Kelvin. So note that I use Kelvin. I didn't use Celsius. I didn't use Fahrenheit. I didn't use Rankines. Those are cursed units. Um, and yeah, these are mostly the units that you'll see. Well, I guess like there's also one more thing that we may or may not use. It's called the mole. Um, so that's also kind of standardized. And the reason why we have the mole is because like, like numbers get big and chemistry people when they want to talk about 10 to the 23 things, um, it's really convenient. And like and like it's something that I think is really cool because like somehow humans discovered this like magic number that's like 20 zeros, like literally 20 zeros. Like there's so many like there's 20 zeros amount of atoms in a teaspoon of like carbon, like or a teaspoon of water. Like if you just take like like this bottle of water has 20 zeros at the back. Um and it has like the same amount of zeros as if you have a teaspoon of water. Well, like kind of like plus or minus two zeros. But then again, like how do we get to that kind of scale, which is crazy? So like that's why we have the mole. The mole like lets us talk about these numbers really easily. Um, there's also the cannula, but we don't worry about it. Yeah, mostly it's gonna be six. Like actually it's seven, but just don't worry about it. Um, yeah. So sometimes you'll see these units. So personally I don't like current. Current sometimes is a bit it's a bit mafan. Like it's kind of in a way because like current, if you want to get charged, you have to get, because like mostly you talk about charge, right? Like current, like for example voltage is the energy per charge. And for example capacitance is like charge over voltage. So you see that people keep using charge in like definition of things. So it's kind of iffy to have a current there. So some people like they like to use this system of units, which is totally the same, totally equivalent. So now I want to show you guys why we call it dimensions. The reason we call it dimensions is because just like linear algebra. So I'm not sure how many of you have taken linear algebra or like will want to take linear algebra. Because like I think it's a great, like in high school if you have free time, I would highly recommend taking like reading like or getting started on linear algebra because that stuff will help you for like decades. I, and I'm feeling its effects right now. So okay, a theory in linear algebra is that so essentially all these SI units are a basis vector in a high dimensional space. So like right now you have a six dimensional vector space. So this is one dimension, two dimension, three, so like all the way down to six dimensions. So there's a theorem that like if you still have six independent um um vectors, then they still are the basis for six dimensions. As in, so let's look at a little smaller example. So if you have a three-dimensional space, and you have three vectors, for example, you have vector here, vector here, vector here. So these vectors, they're gonna still like combine, like you can still combine them all together to make vectors that go anywhere in 3D space. For example, if I want to go here, I can like I can be like, hey, go here and then go here and then maybe go there a bit. So that's three vectors lah. I can also say like you can go up here and then maybe go down here a bit and then go back up and then you can get to this vector. So as in like it doesn't really matter how you express the vector, as long as you have enough vectors, you can go anywhere in 3D space. So which is really cool. Essentially, long story short, unless it's some weird situation, you can more or less like switch one of these out and change it with a combination of the other ones. So over here, you can say charge is equal to the current times time, and that still makes a complete set of units. So does that make sense? Like, sorry for the like random tangent to vectors, because then again, like linear algebra is like really it's everywhere. It's beautiful. Okay, hopefully that makes sense. So if at any point it doesn't make sense, please let me know in the chat or just unmute. That's much faster. Because the point of the whole Zoom is to like let you guys have more interaction and like ask any questions that you have. Okay, so let's see. Cool. So as a little exercise, actually like no, I don't think we have enough time for that. It's okay. We can just actually no, we do have time for that. So let's think about like a little let's make a little table of like fundamental constants lah. So we do have six SI units. How about we think of what other constants there are in the world? So a very famous constant in the world is called the speed of light. So the reason why this is so popular is because, like, I mean, number one, like, light is something that's already crazy to think about. Like the fact that we see things that are bright, we say, "Oh, I know what you are." Like, how do you know that? Um, Secondly, like, it's also really cool because it revolutionized the whole of okay. Oh yeah, so we have that Stephen Boltzmann. But yeah, like speed of light kind of revolutionized all of relativity and stuff. Um, but yes, like as Joey said, Stephen Boltzmann is a good constant, but as you will learn like down the line, Stephen Boltzmann is actually a combination of other fundamental constants. So it's a great point to bring up, but like maybe you could like leave that for in the future because that's not really a fundamental constant. So like I was thinking more like Planck's constant. So so like um more basic more basis fundamental and also Boltzmann constant. Like Stephen Boltzmann is made of also like the KB. Oh, sorry, I didn't see the chat. Yes. So yeah, there's also Planck's constant that okay, again is also revolutionary. Like it's the gradient of energy versus frequency. So if you have so the gradient here is just h. Um, so like someone discovered it. Let's see what else. Okay, so that's also gravity, Newton's gravity. Um, Boltzmann constant. And also the two electromagnetism ones, permittivity, permeability. Okay, so we have six fundamental constants. How do you find the units of them? So then again, the reason why I chose these constants is because these are the fundamental constants. Like you can't like these are by definition like we found these constants from many different ways that um we did experiments, we did like theoretical calculations. There's many ways that we got to the same number, and it's like the universe seems to like these numbers. Um, so these are the fundamental constants. And okay, so let's think about it. Like, what's the units of these things? So number one, speed is like like speed. It's quite straightforward. Speed is just meters per second. So I'm okay. From now on, I'm gonna write all the units in this weird square bracket because people you can also use like meter, like mass, length, time, but that I don't really vibe with that because like it's kind of like a out of comfort zone unit. So I like to use like meters per second, like kilograms per I don't know kilograms per number or something like that. Kilograms per mole. So yeah, so like speed of light is just meters per second. Planck's constant. How can you find the units of that? So um. One of the equations that Planck's constant is like involved in is the definition of the energy of a photon. So the unit of energy has joules, which is again joules. It's a made up. All right, I forgot to say something about this. So, um, yeah, joules is it might seem like a new unit, but actually deep down, it's actually a combination of these six units. These are the six basis units. Um, So joules is actually a combination of all six. Just like how a vector in a six-dimensional space can be written by any sum of the six vectors, a joule can also be written as a combination of all these six vectors, all these six quantities. Um, so I will not show like how, but I'll just say that this is kilograms meters squared per second squared. Um, and this h that we want to find, and then frequency just has the units of per second. And so if you simplify it, you get H has the units of kg meter squared per second. Um, so again, if you haven't taken quantum or anything similar to quantum before, don't worry about it. This is kind of like a quick introduction to like the different fields of physics, and the numbers that you will see in them. So Planck's constant is a number that you will see in quantum physics. Um, but why would you see that in quantum physics? Well, um, a reason why is because like if you don't know anything about quantum physics, like but you know like mechanics, right? If you know mechanics but you don't know quantum, if you look at Planck's constant, there's something very peculiar there. If you look at Planck's constant, there's something very peculiar there because this is also the units of another mechanical quantity. So specifically, what is it? So I'm gonna give you a hint. It's gonna be angular momentum. And so if you look at the definition of angular momentum, if you've seen it before, or maybe like let's just use a simpler, yeah, like maybe you've seen like this definition of angular momentum before. So what is this? So this is kilograms, meters, meters per second, and so you get this to be kg meters squared per second. Hey, it has the same units as Planck's constant. I wonder why. So yeah, like it's like like even without knowing quantum mechanics, like these little like connections they make like something fishy going on there. So yeah, I think like like having thinking in terms of units is a great skill. And yeah, like you'll really benefit from that if you like always check your units. Um, like not just for sanity check, but also like to motivate your thinking. All right, so Newton's gravity. So this G, it shows up in definition of a force. But since we're only looking at units right now, I don't really care what that force is. I'm not doing any actual physics. I'm just looking at the units. So force has units of mass times acceleration, because F equals ma, but not always ma because it depends on like the situation. Um, it's a sum of force that's equal to ma. But anyways, so this g, and you have a kg squared at the top, and then you have a meter squared at the bottom. So g works out to be kg meters cubed per second squared. Cool. Okay. Um, I think I'm gonna. Well, okay, I'll do one more. Boltzmann's constant. So Boltzmann's constant is a quantity that can be used to express like statistical physics. It's like it's a number that shows up a lot in thermodynamics when you talk about energy and stuff like that. Um, and specifically, um, it's related to the average energy of a system. Like, which is really cool. Like something I really love about thermodynamics is that like you don't have to talk about anything detailed about the system. You have to talk about some details lah, but you not knowing fully like how the system not knowing fully the system at every point in time, you can still get like aggregate statistics about the system. For example, you can't talk about what specific energy a system is. Well, maybe you can, but like it's computationally intensive. You can't talk about like the energy like specifically of this system at this point in time, but you can talk about the average, the mean of the energy over time. Um, so yeah, like something that will pop out if you do this analysis is Boltzmann constant. Um, so specifically, if you've seen it before, if you have a so something cool about thermodynamics is that you don't have to specify the system. The same and same equations can hold for any different system. It can hold for I don't know, particles in the box. It can also hold for stars in the galaxy. Um, it can hold for bodies of water in the sea. So it's like it's really general. And something that you will see in if you take maybe A-level physics or like SPM physics, it's like the equipartition theorem. So this is the average kinetic energy of a particle in a gas. And so from this equation, you can kind of guess that KB has units of energy over temperature. So then again, like since we know the units of energy, energy is just meters squared per second squared per temperature. Okay, cool. Um, is that okay for everyone? Like, am I going too fast? All right. If I am, again, that's why you guys are here. So just let me know. Okay. So why do we talk about these things? Why do you talk about these six fundamental constants in the first place? Well, number one, it's not because they can also span the six-dimensional space. That's not true. Like even though I said that like you can replace these with a combination of so you can change any six. So you have six. You have a set of six, right? You can always like choose some of them to pair up together and then replace one of them. So for example, I paired up current and time to get charge. But you can't do that here because the thing is like in this six groups of units, you don't have mole here. The mole does not exist. I mean, you can also do this yourself, like permittivity and permeability, but you'll see that quantity does not show up. So it's actually a five-dimensional space. Isn't that sketchy? Isn't that sketchy? Like, so where did the last one go? Like, if we have, so if I said that you have six vectors you can use that to mix and match to get any vector in a six-dimensional space. Why is there six here, but I still can't get everywhere? So the fishy business comes from the same equation that revolutionized relativity. So there is actually, yes, so the E and mu, the permittivity and permeability, they're actually related. How are they related? They're related with the speed of light in vacuum, that is. So yeah, because there is one more relation, you kind of constrain one of them. So because you know this one equation, you kind of it's like when you have six unknowns and you have um six unknowns and you have um wait, sorry. Wait, I mean like it's like if you count so yeah, if you have six unknowns, but then you have one equation that like constrains the three of these the relation between these three um so like six unknowns, one constraint, you actually bump it down into five unknowns, five effective unknowns lah. So these two combine together, and then you still get like five independent vectors, five independent quantities. And so yeah, like it's another way to look at it's another way to look at all the units that you'll ever see. EP and mu. Oh, what does EP mean here? Sorry, Jungwei, I don't think I understand. Yeah, well that's yeah. But what do you mean by EP? Is that potential energy or is that yeah, I do. Sorry, what's EP? I don't sorry, I see. Okay, gotcha. But it's not Maxwell Boltzmann though. It's like it's this the relation of speed of light. But you get the right idea though. You got the right idea. Cool. So anyways, let's not dwell too much on this because we have limited time. Um, we okay. Why what something else really cool that I want to show you guys. Oh wait, sorry. Before that, um, let me show you an example. The reason why this thing is so cool is that you can just kind of guess your physics. So the reason why we talk about units at all is number one, it's a sanity check, but secondly, it's a great way to guess the answers without knowing anything. For example, suppose okay, so now I'm gonna give you guys an example. Suppose there's this physics problem that asks you to find. So you have a cloud of gas, you have a cloud of gas somewhere out in outer space, and you have a dense. So this gas cloud has a density. So um yeah, like density of like how much particles there are in a given space lah. So we know the density. We know around how big it is because you know you can use a telescope and look at it. So you can ask like a question that you can ask is like how like so particles are gonna attract each other. So they're gonna like um go towards each other. So like at some point this gas cloud is gonna shrink and shrink and shrink and shrink and shrink until it collapses. How long is that gonna take? How long is that going to take? So that's a question that you can pose. So how do you answer this? There's a few ways that you can answer this. There's a way that you can answer this with Gauss's law. Um, there's a way that you can answer this with Gauss's law, write down blah blah, you get G, and then from G you can get blah blah, F equals ma. So the F equals dma because you know like different layers have different mass. Um, because of how big they are. I mean, I know the density is constant, but you know, like if you have a bigger radius, you have bigger mass. So, anyways, if you do it the actual physics way, you have to write down you get the you get the gravitational field, you run the F equals ma, you integrate, you get the time. So it's a lot of work. We put this at the first lecture series is because we hope that you can spot more of these time-saving shortcuts. So what do I mean by time-saving shortcuts? So it's dimensional analysis. So let's write down what we expect. So we expect to get a time out of this, right? So I'm just put a big cross because you know we don't do that. Like for this lecture at least. Like you hopefully you can learn how to do that in the future. But but for now, like let's just look at how you can kind of skip the answer. So we know that at the end of the day, you're gonna get a free fall time, like um the time that the gas cloud takes to collapse. Well, this is called T, big T. So we know there's a time involved. We also know that the density and radius is probably going to be involved because, like if you have a bigger density, if you have a bigger gas cloud, it's going to take longer, right? Like, does that make sense? Like, if you have maybe we don't know yet. Maybe it might be constant. Maybe it might not depend. We don't know yet. We just put it in there. Density. If you have a higher density, the more mass there are, like they will attract each other more strongly. So that's definitely gonna affect uh the time. One last thing that we haven't included yet is the effect of gravity. Because like this thing collapses under gravity, right? So how do we like none of these things scream gravity. This thing screams time, this thing screams density, this thing screams size. So how do you add something that screams gravity over here? So the reason why we have these six fundamental constants is because these kind of um these kind of encode the effects of some fundamental physics in them. So it's a really abstract way to say this, but essentially, if you think about it more, you will probably need G in your calculations. Does that make sense? Like this leap. Like the reason why I include G is because I know there's gonna be gravity there. So I'm gonna put it there. And yeah. Let's time has units of seconds, density has mass per volume, radius has length has units of length, and the gravity from just now, we got that this is per kilogram times meters cubed per second squared. Does that make sense to everyone? Like, per second squared? Yeah, per second squared. Okay, so how do we use this to our advantage? So you can write so because we know that at the end of the day we're gonna have this time equal to something something something, right? Hello. So on the left we're gonna have seconds, and on the right it's gonna be a combination of rho, r, and g. Which combination makes sense such that we have seconds? So right away I see that seconds comes from here. Seconds only comes from here. There's no seconds here. There's no seconds here. So if there's any seconds going to appear on the right hand side, it's going to have to come from g. So I'm going to have a square root 1 over g, right? So what does this have? What units does this have? So 1 over square root g. So yeah, 1 over g. So like the square is like outside lah. Um so if you have 1 over g, it's just going to be kilograms per meter cubed. Does that make sense? I'm just inverting this. And also second squared. Mm, yes. Yes, yes. Yeah. And then if you want to eliminate this kilograms meters per meters cube, so let me just remove the square root because like we know that we're gonna get s squared. So let's leave that at the end. So if you want to eliminate this kilograms per meter cube, that's where the density comes in. And it has to be density. It cannot be radius. The reason why is because if you want to eliminate this kilogram only shows up in the row. I mean I know it also shows up here, but you've already used this. So yeah, the kilogram only shows up in the density. So now this rho g has units of seconds squared. And so the whole time it's 1 over rho g, which is really interesting. Realize that we don't use the radius at all, which is totally fine. We don't know anything yet. So like just now, I was kind of like tricking you guys, like, maybe a bigger one will have take a longer time. But actually you do the math, you realize that it doesn't. Which is really interesting. Isn't it interesting? Do you guys think it's interesting? If you think it's interesting, can you give me a reaction? No, I mean like, but it is something like that's really cool. You don't do any physics, you can still get the answer. Um, like you can still get like the same result, even if oh okay. So the caveat here is that you don't get the exact result. You get a proxy for the exact result. So as in like you get something that's proportional to the result. So you don't know if there's a pi here. You don't know if there's a 2 pi here. Uh, you mean like congruent to the actual answer? Like because the actual answer, like, so if you do the honest physics, if you do like this honest physics, like go down this line of reasoning, you will get something that's like t equals like twice. I mean, I don't know. Like the thing is, I don't remember this. So the things like I don't remember this. Like I've done that before, but I just don't remember the solution because there's like some numerical prefactor in front. There's some number in front that I just kind of like ignore in my head, which is kind of bad. But like there's some I just don't remember that. But what I do remember is that it has this form of 1 over rho g, and I think that's all that matters. Like because yeah, like so as in like the actual answer is gonna be some number times this square root stuff. Um and you can get so close to the answer. You don't have this number in front, but you can get so close to the answer just by looking at units. Oh, sorry. It's my bad. You can get so close to the answer just by looking at the units. Yeah, so that's one application of thinking in terms of units. Like, any questions so far? Cool. So, okay. This is a very cool method, right? This is a very cool method. I hope you guys agree. And I'm gonna tell you guys one more method, one more thing that can really help you think in terms of this method. So this method called dimensional analysis, you can further superpower your skills by having this one more theorem called the Buckingham Pi theorem. So before we start this, I'm just gonna like say that. So before we start this, I'm gonna tell you another way that you can arrive at the same result. So one way that you could arrive at this result is that you can say, okay, I expect a seconds on the left. What should I have on the right? That's one way to like write down this equation. Another way to write down this equation is to say that okay, t square root rho g has no units. T square root rho g has no units. Therefore, this thing is gonna be some number on the right, like it's like 10 or pi or something. I don't really care. I just put one there because one has no units and one is a simple number. So therefore, t is 1 over the square root of rho g. That's also another way that you can get to the same answer. So I mean, these are the same thing. These are the same thing, but as you can see, this has a different way of thinking than this. You know what I mean? On the left, you're trying to make a seconds appear. On the right, you're trying to make nothing appear. Does that make sense? Is that okay for everyone? So, yeah, so in the Buckingham Pi theorem, we focus on these dimensional units. We use this approach. We use this approach of trying to make things that have no units. So, okay, so I'm going to state the theorem. The theorem says that if you have, sorry, the theorem states that if you have n quantities, but you have k dimensions, then you can form n minus k dimensionless quantities. So, like, what does this mean again? So, okay, let's see. Over here, in the example just now, we had 4 quantities. So n equals 4. We have 4 things here. N equals 4. So what are the dimensions? There's a seconds, there's a meters, and there's a kilogram. The third one is like doesn't matter because like it's a combination of the first three. So as in, like like, you already have seconds, kilograms, meters, and then there's just a combination of the three. So k equals 3 here. Um, something I have to say like sorry, there's some ducks. I don't know, bro. Anyways, something I have to say here though is that these dimensions have to be like the independent dimensions. So what I mean by that? So for example, you can't have force and then mass and then accelerate. Well, okay, you can, but suppose yeah, so, like for example, you have like let's see, and maybe let's just use. Oh, okay, yeah, maybe G lah. So yeah. So okay, let me just use this example. So if you have these three sets of numbers, since we know that f equals ma, we know that these three things are related. But like, suppose you don't know that. Suppose like you're trying to write down f equals ma. but you don't know that yet. So just by looking at these equations, you might think you might think that oh we have so you might think that oh we have three quantities and we have three dimensions, kg, meters, and second. It's not true. We only have two dimensions here. We only have k equals two dimensions here. The reason why we have k equals two dimensions is because this one thing, this is one, it's all grouped together. We can't separate them. We don't know like we don't know the difference between meters and seconds yet. I mean in this example, in this specific example, we don't know the difference between meters and seconds yet. Because meters and seconds are coupled together. So unless you have something like, I don't know, like time, so you have a seconds, then you okay, now we know the difference between a second and a meters, and a meter per second squared. So now we have one, two, three different sets of units or dimensions. So yeah, just a note that these are independent dimensions. Okay, so right. We have n quantities, k independent dimensions. We will have n minus k dimensionless quantities. Why is that important? The reason why it's important is because the Buckingham pi theorem says that these n minus k quantities, you can say like pi 1, so we call it pi lah, because Buckingham pi, the pi comes with this pi. So there's pi 1, pi 2, all the way up to pi n minus k. It's going to be your dimensionless quantities. What Buckingham says is that the combination of all these is going to be unitless, which makes sense, right? Like dimensionless quantities, if you combine them in some other way, it's still going to be dimensionless. So essentially what it's trying to do is this. Essentially what it's trying to do is to say that let's make something that has no units and then we can get to the result. This is what Buckingham pi theorem is saying. Let's make something that has no units, combine them together in some way, then we can get a result. So normally in the cases, it's not normally in like Olympiad settings, like simple problems, this n minus k is sometimes just equal to 2. So it's not always true because like again, the world is big. There's many phenomena to study, but in a more like simple regime, in a more Olympiad physics regime, n minus k is normally 2. So you will normally only have pi 1 and pi 2, right? So normally you only have pi 1 and pi 2. The Buckingham pi theorem will say that pi 1, a function of pi 1 and pi 2 is going to be like some dimensionless quantity, which is to say you can invert this relation to get pi 1 is a function of pi 2. Um, I mean, again, these f's are not the same. I'm not going to use a different f for this, just to really bring home the fact that it's just some like so for example, this f pi 1 pi 2 could be pi 1 plus pi 2. Right. So like and then I can just always rewrite this as like pi 1 is equal to 1 minus pi 2, which is just another function of pi 2. You know what I'm saying? Like as in like you don't it doesn't really matter like what it doesn't really matter what the small f is. It's just like some combination. Which you can always invert to get yeah, this other form. Well, like there's some nuances, it's not always invertible and like there's like some transcendental like just don't worry about it. Um yeah, don't worry about it, guys. Cool. So let's see how this can be useful. So as you can see, from here, we already know like how useful it can be lah, because four equations minus three, that means oh that's one dimensionless quantity. If we have one dimensionless quantity, that means that we can just set that equal to one. So that's easy. What about a case where you have two dimensionless quantities? So let's see. Let's look at another example. Suppose I'm making a paper helicopter. Suppose I'm making a paper helicopter. Um, this thing has radius r, a weight w, and is dropped by height h to an air density of rho. Okay, that's a lot. That's a lot to take in. But let me just recap for a second. So you have a paper helicopter. You drop it from the air from a height h in an air of density rho. This paper helicopter has radius r and weight w. Assuming that the helicopter quickly reaches terminal velocity, how do you find the total flight time? So I want to find total flight time. Is that okay for everyone? Okay. So firstly, do we need G or not? Yes or no? Do we need G or not, guys? What do you guys think? Should we include the gravitational constant here? Careful, guys. I will ask trick questions sometimes. So, okay, well, okay, I see people like answering in the chat. Okay, well, the answer is no. The reason why it's no is because like G is already in here. Yes, that's right, Kahin. So, so yeah, it is a trick question. So, sorry for being tricked. But yeah, okay. So you don't need G here because weight already has a manifestation of G. Because like weight is just like mass times gravity, right? So weight already like has something encoded in the it already has something encoded in it. Okay, so how do we do this? So let's write down all the things that we have. So we want to find time, right? So what do we have? We have weight, we have mass. Oh, sorry, we have weight, we have radius, we have height, we have rho. 54. Yeah, we have these five things. So again, the total flight time we have as what's the units of weight? It's just units of force, right? So what's the units of force? So it's just like kilograms meters per second squared. Radius has units of length, height has units of length, density has units of kilograms per meter, minute per meters cube. Okay, can someone tell me n equals what? N equals what? So what's n and k here? Friends, friends and enemies. No, okay, I'm kidding. There's no enemies here. Everyone's a friend. So what's n, what's k? Guys, there's no wrong answers. Well, actually, like, there's a few wrong answers, but like, it's like negligible. Yes, n equals 5, k equals 3. Thank you, Zhongwei. N equals 5, k equals 3. So, how many dimensionless quantities do we have? 3, 2, 1, go. N minus k, what is it? 2, let's go. Okay, so we have two dimensionless quantities. Right away, something that's easy to see is that one dimensionless quantity is r over h, because these two have the same units. R and h have the same units. So right away, pi 1, we can write as r over h, or h over r, it's up to you. Doesn't really matter. H over r over h, doesn't matter, but just be consistent. You can't just halfway through make it r over h. Like just make sure like you use the same. Yeah. So hell yeah. So what's the other one? So the other quantity we can get from the weight. So, okay, so now that we've used this, let's kind of like put this away and try to see if we can make a dimensionless quantity out of the first three. So let's see, how do we make something that has no units? So right away, there's a kilogram here, there's a kilogram here, we can cancel them out. If you have weight over rho, this thing has units of meters fourth over second squared. Yes, yes. So, um, the second square I can take away if I multiply both sides by the time. And so I'm left with meters to the fourth. Hmm, sus. So, hmm, which one do we use here? Is it R or is it H? It doesn't really matter. But I would just use R first because like R is like kind of the size of the rotor. So this should be equal to what? So pi 2, sorry. So pi 2 has no units. Mm-mm. Oh, N represents how many quantities you have. Yeah. And K represents how many independent dimensions you have. So over here, N is equal to 5. k is equal to k is equal to 3 because like there's seconds, there's kilograms, there's meters. So k equals 3. Yep, no worries. So pi 2 here is just w over rho t squared over r to the fourth. Okay, so okay, again, let's remind ourselves what we want to find here. Let's remind ourselves what we want to find here. We want to find the total flight time. We want to find how fast it falls down. Also, I think something I forgot to say is that we're assuming this reaches terminal velocity really quickly. So terminal velocity is reached really quickly. So how do you find the total flight time? We're still looking for the total flight time. Don't forget that. So yes. So let's see. Okay. Will this? Okay. So wait a second. So now we have the two-dimensional quantities. We can write pi 2 is a function of pi 1. W over rho t squared over r to the fourth is equal to some function of h over r. So we don't know what the function is, right? We don't know what the function is. How do we guess this? This is kind of tricky, right? Anyone has any ideas how we can guess what f should be? Let's think about it for a while. We used Buckingham pi theorem. We got pi 1, we got pi 2, we got all the way to this point. How do we guess the function? So let us think for a bit, because I've been yapping for a long time. It's gonna bite out my croissant. Okay. So everyone has had time to think through this. Okay. So I'm gonna tell you guys right away. There's no way to get f. Let me use a theorem. Oh, great question. Yeah, that's a great way, but then again, like it's kind of circular reasoning, right? Because the way you got this f was using the Buckingham pi theorem. So you can't like as in like you got so like this is all the things you have. You got all the way down here, and then if you go back up again, like you just get back to where you started, right? So that idea may or may not work. Um, mm. but I'm just gonna say right away, you cannot get F without thinking of something else. So it's well okay like you can still guess F. You can still guess F, but you have to think of something else. You have to actually use your physics intuition. You have to actually impose things of the real world to get to the actual F that you want. So what do I mean by that? So this is as far as dimensional analysis can get you. We're at the horizon of what we can see. We are at the horizon of what we can see here. This is as far as it can take you. It cannot take you farther. It can only take you as far as this. You, as physicists, has to kind of guess what this F can be. So, remember how I said this is terminal velocity? So what happens in terminal velocity? Can someone tell me what terminal velocity means? What does terminal velocity mean? Yes. So what does that imply? That's right, constant velocity. Newton's first law. So that means that constant velocity. So how do we like what should we expect? If it's terminal velocity, we should expect h to be something times time, right? The flight time should be proportional to how far it has to fall. Does that make sense? Because it's constant velocity. H is equal to something times the time. Is that okay for you guys? Does that make sense? Because like so this thing is actually just velocity, but I don't want to write it because what I really want to show you guys is this thing and this thing has the same power. As in, like, this thing is not under acceleration, because if it's under acceleration, then it's going to be proportional to t squared. It's under constant velocity, so that's why it's proportional to t. So that means that whatever this function might have to be, it has to make sure that h and t have the same power, right? So that means that f is probably x squared. Sorry, f of x is probably x squared. So W over rho T squared over R fourth is probably H over R squared. Why is it squared? Again, the reason why is because we use a physics intuition. We use another reasoning from the outer world, from the external world. We use this reasoning that terminal velocity should have H and T have the same power. We expect these two things have the same power, to have power 1. So if you put them to be H squared, then you'll see square root of W over rho T is equal to H R. Yes. Sorry. Yes. No, sorry. R squared. No. Square, square, square. Yeah, 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 sorry. Yeah. Wait, no. Yeah. W over rho. Okay, yeah, yeah. It is right. Oh, sorry. Yeah, sorry, I was too carried away with the math. Anyways, yeah, because we use our physics intuition, we should impose the same thing on the H and T, and therefore we can rearrange this to get rho over W. So that's total flight time. Yes. So wait, sorry for I got carried away with the math. But yeah, this should be the answer. The flight time should scale linearly as the height, and also linearly with the radius as well, which is interesting. Um, so yeah, again, let's check if it makes sense. Let's check if it makes sense. If you have a really heavy airplane, so this W goes to infinity. Suppose you have really like you have like big chunkers on there, like it just falls like quickly. So you have yeah like yeah. So this thing is gonna have W be really big, and T is gonna be really small, which makes sense because if you have something really heavy, it's gonna fall really quickly. Um, So something else. Let's see what else. Density. So if you have a very dense medium, if you have a really dense air, then it's gonna be like that's gonna be more drag. It's gonna go like slower. So this rho is gonna be like so if this rho increases, time also increases, which also makes sense. Um. So yeah, I think this equation makes sense. And this is part of the Buckingham Pi theorem. The power of the Buckingham Pi theorem can only bring you here. But to go further, you have to think of something external so that you can guess what F should be. Does that make sense for you guys? Okay, so let's take a break. It's at 9 a.m. It's at 9 p.m. now. Let's take a 5 minute break and we'll come back and continue with math. So yeah, I'll be around. I'm just gonna be like give you guys a water break. Actually, no, like not 5 minutes. It's just 2 minutes. Like we have quite some ground to cover afterwards. So let's make it quick. Thank you guys. But yeah, like use this time to think about what you just wrote, or what you just saw. You can ask me to scroll up, scroll down, just tell me, and we can have any discussion in between this time. Okay, so let's try to yeah, hopefully we can wrap up this section and we can move on to the next one. So as a wrap up, let me just kind of like clarify something that I realized some people were asking in the chat. So the jump from here to here, how do we jump from h over r to h over r squared? So the reason why we did this is because again, from our intuition, we know that this is what we expect. We don't know what this thing in the middle is going to be. We don't know yet, but we do know that h should be proportional to t to the 1. Or, equivalently, t should be proportional to h to the 1. Like, it should be linear in the height. Like, the answer lah. Like, at the end of the day, once you do all this math, you should expect t to scale as h to the 1. So how do you do that? Because, like, if you expect this, then you're saying that this t squared, if there's a t squared on the left, there should be h squared on the right? Because otherwise the power is not gonna be the same. Like you have t squared on the left, blah blah. If you want this to hold, then that means that there's gonna be a h squared on the right? So that's why if you see a t squared here, then that's why you know that there's gonna be a h squared on the right. H h squared. Yeah. So the one. So okay, is that okay for everyone? Like okay. So okay, as a final thing before to wrap up the section, I will say that Um, even though it might look like everything in the world has units, which they do, everything in the world has units. In the math world, you can always write all the equations in terms of non-dimensional units. So dimensional analysis applies everywhere. If you have an equation that has, for example, e to the something negative x, so this thing here has to be dimensionless. Otherwise, it's not going to work. For example, I'm just going to post some examples. If you've seen it, you've seen it. If you've never seen it yet, don't worry about it. So I'm just gonna post an example, so don't be scared if you've never seen it. So for example, the density of the air as it scales with height. So density of the air as it scales with height has this kind of form. So you can write on the left, this density of a density has no units, right? On the right here, this is energy over energy. So it's mgh over kT. So this is energy. This is energy, and they cancel each other out, no units. So yeah, you will always see things that have no units in physics. Like not just this, but you can for example, let's say for example, let's say uh V so like, let's say some calculus stuff lah. Suppose some calculus stuff. Um let's say I don't know, okay, maybe acceleration is equal to well okay, oh yeah, great idea. So we can use angular momentum. So for example, if you have vectors, if you're doing math with vectors and like suddenly you're like, oh, what's the units of this vector? So this thing here has like units of angular momentum. This thing has units of mass. This thing has units of momentum. So you can see that this still works, even though it's in vector form, because every component of the vector has to obey this law of like units matching. So like, if you mash them together, the units also match, even if it's a vector. So stuff like that. Sines also, if you have a sine of x, so let's say if you have a standing wave, sorry, if you have a progressive wave. So if you have a progressive wave, so this thing is units of radians, which is basically unitless. If it's radians, that means that it has no units. So this thing also has radians. So you can see that this thing also has like no units inside and then no units on the left. So as in, like you can always write things in terms of like dimensionless quantities. So this would be pi 1, this would be pi 2, some function of that at least. So yeah, you can always write any equation that you see in terms of dimensionless form. Um, yeah, even integrals. If you have integral from 0 to infinity, um, e to the negative. ax squared dx. Um, so okay, let's say this x is suppose this x is some length, some length. Um, and so if you integrate this, you should so suppose x is some length and a is like so what unit should a be? Um, no, wait, that doesn't work. Zhengwei, that doesn't work. That example doesn't work because x and ct have units of meters. The point of this example here is to show you guys that um I think okay, maybe if you want to like use Zhengwei's example is k x and ct lah. But this k is very important. It's not the fact that it's x and ct. The fact that there's a k there is very important. The k here makes everything dimensionless because this k has units of 1/meters. This k has one units of 1/meters, and then this x has units of meters. So that's why they cancel each other out. So yeah, that's the point of this example, is to show you guys that everything inside the function, everything inside any function has to be dimensionless. If it's inside this exponential function, this thing inside is dimensionless. If it's inside this sine function, this thing is dimensionless. So yeah, like the point is to show that everything inside the function has to be dimensionless. So yeah, sorry. Anyways, so suppose you're writing let's say I okay, let's see like integral e to the negative ax squared dx. So if x is a length, this thing is just gonna be end up having units of length. The reason why is because if this equation describes anything close to physical, if this equation describes anything physical, it will have to have this thing be dimensionless. So as in like you don't have to worry about the dimensions up here. The dimensions up here are gonna be fine. Dimensions up here are gonna match because a has to have the right dimensions such that it cancels out with the x squared. So if x is some dimension of of some length, since we know that this whole thing up here is dimensionless, this whole thing will have no units, and the units will only come from this dx here. So that's why the whole integral will have the units of meters. Does that make sense? I think this is a quite weird example, but I think it's a quite interesting example. Hmm. Because exponentials have no units. The whole thing, even though there's like some intricacies, there's some complexities in here, like ax squared and negative, like even though there's stuff going up there, if I take the whole thing, it doesn't really matter because the whole thing has no units, and the only units are going to come from the dx, so it's going to be length. So yeah, I guess that's a wrap up for this section to show you guys that it literally is everywhere, and you literally have to think of everything having units. Um, just so you don't make any mistakes. Like if you see an equation, a great question to ask first is like, what are the units of this thing? What are the units of that thing? It's a great thing to like probe your understanding because yeah, like if you see something has the units of meters per second, you might start to think like, oh, suspiciously that has the units of speed. What speed is this? Then you can ask, and then you can learn more physics, and it's always a useful tool. For example, I think last year when I was applying to get a research position, like the guy was like, yeah, so if you take this like weird astronomy quantity, I was like, oh, what is that astronomy quantity? And he's like, oh, this is something with like units of 1/steradians. And I was like, oh, so that's like how much you can see in the sky. And then said, yeah, 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 yeah. So like, you can always learn something new just by looking at the units. Like um something really cool, superpower. Cool. Um, I'm gonna skip over the case of easy cases, but essentially easy cases. So because I'm gonna send you guys a handout afterwards. Um, oh, sorry. Is it true that the resultant thing? Yes, totally, Isaac. That's the point of this whole exercise. Yes, that's right. You're getting it. Yes. So yes. So anything in terms of a function, everything that's inside the function always has to be dimensionless. If the equation is anything physical. If the equation is anything physical, so like if you talk to a math major, they don't give a shit lah. But in the physics world, if you want to write down a good equation, everything inside the functions have to be non-dimensional, has to have no units, and that's the beauty of this. So where is my shoe? Oh, my shoe is there. Okay. Yes, yes. So the reason why it also applies for polynomial functions is because if, for example, today it's like f of x is equal to like I don't know, 1 plus x squared lah. If this x and this x don't match the units, for example, if you put like x has some unit of meters here, then this thing has like no units. This thing has no units. This thing has units of meters, and then this thing has units of meters squared. So doesn't make sense. If you have a like polynomial function, like f of x equals to 1 plus x squared, if this x is not dimensionless, then you see that, oh, there's some unit mismatch here and like syntax error. So yeah, sorry, not type error. It's not it's a type error. So yes, everything inside any function has to be dimensionless. Mm-mm. Oh, then that like there's because like for that one it doesn't really apply because well x can be anything, right? So for that one x can be as like there's no type error because the type error comes from this like when you add things of different dimensions together. Sorry, yeah, type error comes from here. But if your equation is just x squared, then yeah. So right, it brings us into a great example afterwards. Thank you for asking this, Isaac, because I realized that I can also talk about this in another way. So, um, the reason why, okay, so the reason why you have to have dimensionless quantities in exponentials and sines is precisely because you can always write, so this is going into our next part, math. So, wait, first part, expansions. So the reason why everything inside this function has to be dimensionless is because you can all like everything. So everything, not everything. Like, many functions that you'll see. If you're a math major, don't come at me for this. But many of the functions that you will see can be written as a polynomial function. Many, if not, well, not all, but like many. For example, the exponential x can be written as 1 plus x squared plus blah blah. Sine of x can be written as like x minus x cubed over 3, sorry, 6 plus blah blah. Cosine x can be written as 1 minus x squared over 2 plus blah blah. So every function that you will see can be approximated with a polynomial. Yes, like every function that you'll see. Up to some extent, lah, like it's not an infinitely working, it's not like magical black box that always works. There's some limitations, but it basically works most of the time. So yes. And so the reason why this thing in the exponent has to be dimensionless is because if it's not dimensionless, for example, if E is like, for example, if you put E to the C, whereas C is like the speed of light, if you put E to the C, then this thing has like no units. Then here you have C, which has units of like speed. And then you have C squared, just like units of meters squared per second squared. So you see that immediately it doesn't work because like you can't add something that has no units. Like you can't add something that has no units to something that has units of speed and blah blah blah. Like this doesn't make sense. Wait, I think what Zhengwei is trying to say is the sum of 1 of n squared is pi squared over 6. But um yeah, that's not this yeah. Wait, what? Okay. Anyways, but yeah, this yeah, that's like that. So that's the reason why things in the exponent have to be dimensionless. Oh, sorry, yeah, my bad. But yeah, like what's pi squared over 6? I don't. But yeah, like it's you get the point. But yeah, like so that's why these things have to be dimensionless. If it's not dimensionless, then you see an error. Right. So this idea that every function can be approximated with a polynomial is called the Taylor expansion. So what are some kinds of Taylor expansions? So Taylor expansion is a broad definition, but so this includes stuff like these, stuff like these, and it also includes binomial expansions. So suppose you have this function 1 plus x to the n. You can also express this as 1 plus nx plus x squared plus blah blah. So you can always write yeah, so you can always write even a binomial to the power of n as a function as a sum of like infinitely many polynomial sequences. So yeah, I guess we can skip how you can write this down for now. Suppose you have a really so these are all like really popular functions. You will see these a lot in your career. Um, but how do you write these down? Like so as in like now I know this, like I've seen this before. How do I write the right part down? So if you want to write it down, there's a general formula for Taylor expansions. So the way it works is that if you have a function and you want to expand it around. Okay, so before we go down this route, get let me just see if I can get this past example. Yeah, I realized I prepared this last night, but I forgot to bring it up. So if one goes to if one goes to this link in the chat, which I have posted. What is it? Zoom? Oh, that's me. Cool, cool, cool. Okay, so yeah. So how does the Taylor expansion work? Um, so Taylor expansion, how it works is that you choose a point where you want to expand around. So suppose I want to expand around 0. Then I can say that this is approximately the function at that point plus the derivative at that point, the second derivative at that point. Sorry, oh my gosh, making some mistakes here. Yes, this is the Taylor expansion. So, if you want to expand around 0, what happens is you take the function at 0, you take the derivative at 0, you take the second derivative at 0, take the third derivative at 0, and then you write it as a function of as a superposition as a sum of these power terms. So let's see what happens. Like an example here is that if you have this function sine of x, so sine of x is in red, and if you want to approximate it with a polynomial Taylor expansion, then you can always keep adding terms. The more terms you add, sorry, let's start with one. So like if you have only one term, it's linear because like it's like f of a so f of 0 plus the first derivative. But if you have one more, it's gonna be quadratic. Is it quadratic? Oh yeah, the quadratic. Oh sorry, yeah. It's just 0 because sine. Anyways, yeah. If you have three terms, it's gonna be cubic. If you have five terms, it's gonna be um pentic, and then 7, 9. So you can see it gets better and better at approximating this function. But then again, it still shoots up to infinity because it only works around here in the middle. It only works around here in the middle. Far away, it doesn't work. So that's why I say like this is useful, but you can't always use this. Like you have to like be careful where in what regime you're using this Taylor expansion in. it only like you can always say that this f of x is equal to a polynomial near to some place. So, but yeah, you can also change where this near point can be moved around. So yeah, suppose I want to like talk about the, suppose I want to talk about the point here. Yeah, suppose I want to talk about like this point here as a Taylor series. So how can I expand this point? Expand around this point. So I can just add more terms. If I can make it quadratic, can make it cubic, and blah blah. It's gonna get closer and closer to approximating the function. And I think it's really beautiful. So yeah, coming back here, that's the power of Taylor expansions. You can use this for binomial, you can use this for exponential, sine, cosine. Yeah. Why would you use this in an Olympiad setting? The reason why you would use this in an Olympiad setting is because let's take an example. So suppose you have an electric dipole. So it's okay if you have not learned electric dipoles yet. Just know that it's a plus and it's a positive charge and a negative charge. So suppose you have an electric dipole. Right? Suppose you have an electric dipole. The potential, don't worry about this if you have not learned it yet. Don't worry about this. I'm just gonna write whatever. So this is x equals 0. So this is d over 2. So that's like these two are separated by d. Right. So the potential at any point x is gonna be this potential. So yeah, like if it's a problem just asking you to write a potential down, that's it. So that's like the end of the solution. Um However, it doesn't really tell you much about like what the system is, right? Like it's not like right now, if you've never learned dipoles before, I just kind of like thrown you something called a dipole. It has something related to charge, something related to energy, something related to potential. What am I talking about? So let's see. I'm just trying to show you guys like where a Taylor expansion might be useful. So this Taylor expansion might be binomial, might be exponential, might be sine. We don't know yet, but um, I'm trying to show you guys like it's gonna show up in physics if you talk about like it's gonna show up. So so something useful is because if you have a regime where the x is really small or x is really big, um then you can kind of but if you have x is really small, so when you have x is really small, you can kind of like ignore these higher order terms. Yes. So for example, if x is like 0.00, like if x is already like 10 to the negative 3, which is like 0.001, then this thing is going to be 10 to the negative 6. Then the next one is going to tend to be negative 9, 10 to the negative 12. So like these things you can basically not see, right? The effects here cannot be, yes. Kind of, well, it can be a small angle, but it can also be like small distances, small changes, small perturbations. It can be anything. Like it can even be t plus delta t. Like this delta t over t, like this thing can be really, really small. And so that also works. So it can be temperature, it doesn't have to be angle. So over here, if you're trying to ask someone like, hey, very far away from the dipole, what will you see? So suppose you're like all the way over here. Suppose you're all the way over here, and you want to ask like, hey, what do you see here? There's someone over here. What do you see? To someone far away, it might seem like there's a positive charge, there's a negative charge, so they're gonna cancel out, right? If you're really far away, you see two charges that are really close to each other. It's just kind of like they cancel each other out. So the net charge is zero. But is that really true? So if you say that when x is really, really big, if you approximate too much, then it's just gonna be 1 over x. Because like if x is really, really big, much bigger than d, Then suppose this is 10,000. This is also 10,000. And so, and suppose D is like 1. D is like 1. So this is gonna be like, these two numbers are gonna be really close to 10,000. And you might say, and then so it's like, oh, 1 over 10,000 divided by, subtract away 1 over 10,000. Then this thing will be 0. And you will be right. This is gonna be right if you approximate it to the first order. The first order approximation means that you just kind of like ignore like all the higher order terms. You set everything else equal to 0. You kind of say like your course is like you're blurring your vision too much. Because it is true that at this point, it might seem like this plus and minus charge just kind of cancel each other out. And that's what you see here. If you say that x is really, really big, and you can ignore d. Because if you ignore d, these two things are basically on each other, then plus and minus is just 0. What if you don't? If you don't see that, then you can do some math. So this thing, I can take an x out, and this is going to be 1 minus d over 2x. Does that make sense how I wrote this down? So when I say that d is much smaller than x, that means that this number is much, much smaller than 1, right? It's a really, 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 really small number. So I can approximate this using the binomial expansion. I can use this form and say that this thing is like basically 0 and everything else up here is 0. I just take the first term. So for first two terms. Um, so yeah. So yeah, like this is gonna be 1 plus d over 2x minus 1 minus d over 2x. What does this give us? This gives us, so the ones cancel and the halves cancel as well. So it's like you add two halves, you get one whole. This is gonna be d of x. So v of x is approximately d over x squared, which is interesting. It's not 0 now. So remember just now, like if you say that x is really, really big and we just ignore the expansion, if we just ignore this expansion and just like replace this with x, then we say that 1 over x minus 1 over x is just 0. And then you get a 0th order approximation. So 0th order approximation means that you're not seeing anything. You just like you're approximating too much. If you refine your approximation to get the first order term, so this is first order, then you get a dipole potential lah. So and you can get a second order term, get third order term. So like you get higher and higher terms, but like normally for dipoles, people approximate to the first order. So yeah, like does that make sense? Like how you would use um potential how you would use expansions in physics. Um okay. Cool. In my next example. Okay, so yeah, so like anyways, like the first technique that you guys should know like is expansions and like so so the reason why we put this under thinking like a physicist because like sometimes you just have to see like which ones can be approximated and like assume to be 0, which one you cannot. So in this case, if you're thinking like a physicist, then you have to think of okay, what order should I like work in? Like should I work in 0th order? Because sometimes 0th order approximations are good. You don't need this sometimes. Sometimes you don't need this. Sometimes you just need to know that this is like a small part in a bigger whole, in a bigger sum. So like suppose this is like a subsystem, and like for example, there's two charges and then there's like 10,000 charges next to you. The fact that these are positive and negative doesn't really matter to you, right? So you should focus on the 10,000 other charges. So in that case, a 0th order approximation might be good for you. So it kind of depends on what order you want to. And so this should be viewed as just a toolbox for you. It should be a tool for you. As a physicist, like think of like, hey, can I just go to first order or should I go to second order? Should I go to fourth order? It depends on you, but it's a toolbox for you to like think of like how you can write down which order. Okay. Next thing, calculus, specifically infinitesimals. So how many have you have heard this word before? Infinitesimals. We have not heard of this term before. Oh, interesting. It's not everyone. So p plus not p is not equal to 1. There's some loss in probability here. So, anyways, so infinitesimals is okay. So now we go into calculus essentially. So something I think is really important to in something I think is really important in physics is to keep your head on the ground. As in like there's gonna be a lot of things changing at once. So especially like when we go into the rotational mechanics lecture, this is gonna be especially true when things start spinning, when things start changing a lot, when there's like five different things changing in concentrations, when there's like a top. So, sorry, I'm just writing my song. Anyways, things are going to change a lot. A lot of things are going to change a lot, and very quickly at that. So, a way of thinking that I think is really important is to think in terms of infinitesimals. So, um, instead of looking at the whole thing changing, you only look at one point in time and just vary the time by a little bit. Like, let the time play by a little bit and then see what happens. So, what I mean by this? So, suppose I have this example of okay, so um okay, sure. Let's just think of this example of the circular motion. So in high school, you'll probably learn about like everything in circular motion has to have a centripetal acceleration, right? Everything in circular motion has to have centripetal acceleration. So it's like centripetal acceleration here. So how do you find that centripetal acceleration? So this R, this V, suppose it's V, and it's going around in a constant velocity. So it's just going around, right, round, right, round. Cool. How do you find this acceleration? So this acceleration, you have to think in terms of infinitesimals. 'Cause, like, if you don't think in terms of infinitesimals, you might just think that like this acceleration is gonna be discontinuous because like um the if the particle is here, suddenly afterwards it's here, you see that oh like the velocity changed a lot, right? So this was the original velocity, this is the final velocity. The velocity changed a lot. So you might think that oh that is the acceleration. Um But yeah, like if you don't think of infinitesimals, it's really like sometimes you might just get the wrong answer. Um, so yeah, if you want to find the so infinitesimal thinking is so like I know this example of a circular motion, it should be like you guys should have seen it before, but the, the point I want to try to bring home is that like you can derive a lot of things if you only think of small time scales, if you only think of small changes. So as in, I want you guys to get familiar with thinking of changing everything by a small amount. So before everything changes, like before I think about this, like you just imagine this thing going around in a circle, in a circle, in a circle, right? Like however, like maybe it's a ball on a string, maybe it's a planet around the sun, whatever. It's just going around in a circle. So infinitesimal thinking says that okay, we stop at this moment of time. We stop at this moment in time, and we change the time by a little bit because like time is gonna play and it's gonna circulate a lot. Or we stop it and we change it by a little bit. So how should that look like? So if you pause this and you zoom out. I'm gonna draw a really big diagram here. So this was the original V. This was the original V. And then now, after some time, So the point here, right? So there's a velocity originally pointing up, and then the velocity is going to change to the left. So you see that something is changing the velocity's direction. So this is after some time dt. So this is t plus dt. So this dt is what we call an infinitesimal. It's an infinitesimal change in time. Infinitesimal. Say that word 10 times out loud quickly. Infinitesimal. So anyways, yeah, so after the time dt, the velocity changed by a little bit. By how much? So originally it was like this, and then afterwards it got changed to become like this. Right? So this was initial, and the one on the left is after. So there's a change in velocity in this direction. So there's a change in velocity in this direction. And that's what we call centripetal acceleration. And so you can do some math. You can do some yeah, you can do some math and like just figure out the expression for this. But um I think I don't want to do that. I think the point here is to show you guys that like if you think in terms of infinitesimals, things are gonna be clearer because um uh yeah like because like the definition of acceleration um so because the definition of a lot of things in physics is in terms of the differential equation. Or for example, the acceleration is defined as a change in velocity over time. So um, this is dv. So you can express dv if you think of the infinitesimals, and you can express dt by just thinking of like small time changes. So as like just something you made up. So yeah, if you get like the if you get the infinitesimal change in velocity, then you can directly know the acceleration. So that's easy. So I think hmm, is there more examples of this? Yeah, so like when you do like particle kinetics, this thing is gonna be really useful when you do like for example like particle hmm, okay. So I guess for that example, I want to talk about probability then, because I think like particle kinetics is a little bit too complicated to talk about at this stage. But I think well I'll talk about probability because infinitesimals show up every day in life. Um if you don't use it to write down accelerations or like to express like differential quantities, you can also use them to express probabilities. And because I think SPM or SCPM, well I think SPM, they have this probability density function. So unit probability is something that you sum to one. For example, if you have like 1 6, 3 6, and 2 6 of like event one, that's event two, that's event three. Suppose you have three events. The probabilities are going to sum to one. Which is sure, like cool, it's a discrete probability. But when you come into the real world, when you come into the real world with like continuous probabilities, sorry, continuous like quantities. For example, instead of like having E1, E2, E3 now, the events can be something like, oh, what's the probability of someone being a weight of 60 kilograms? So what's the probability of like someone having a weight of 60 kilograms? Well, like so like suppose you have the whole world, you randomly choose a person. What's the probability that they're 60 kilograms? The probability here should be exactly zero because there should be nothing called an exact 60 kilograms because nothing's exact, right? Like no one's exactly 60.000000000 kilograms. So um so what people do instead is to ask like what's the probability of someone being from 60 kilograms to 60.1 kilograms? So like this 0.1 is our infinitesimal. The n is our zero point 0.1. So this infinitesimal is used in when you talk about probabilities. And so instead of summing to one, you say that the integral of p dn, say, sure, yeah, sure, I'll use n. Probably if you integrate across everyone's masses, you should find the probability is equal to one. Same thing over here. So as in like probabilities can also show up, it's like infinitesimals can also show up when you talk about probabilities of continuous things. Instead of summing equal to one, you have summing instead of summing the probabilities directly equal to one, you have the probabilities multiplied by an infinitesimal. So that's like small probability. So that's like this probability of like someone being in 60 to 60.1 kilograms is gonna be equal to the PDF, which is some higher than like some higher order like probability thing. Don't worry about it. It's some function. Just know that it's some function multiplied by delta m, which is the bin that you're talking about. So over here, this delta m is 0.1. Then use dm. Yeah, so that's another way that infinitesimals are used. Yeah, I guess that, what my point is that like you have to start thinking of infinitesimals so that you can write. Um, so like like probabilities become more clear. You can write down differential equations. Um, and yeah, like it's a really important skill. Okay, I guess finally, mm, what an example for? Yeah, I don't think I have a good example for the infinitesimals yet, but it's okay. If I find one, I'll just post them in the in the channel. Okay, lastly, vectors and coordinates. So um, we know that. Wait, so um, well, okay, so like as you can see from this example before, as you can see from this example before, a lot of things are geometrical, and you want to describe them in like a few ways. So, for example, here, in this rotational example, you can describe this in XYZ coordinate. You can also describe it in terms of a polar coordinates. So, what do I mean by that? So, yeah, XY. So when you want to say, hey, how do they go from here, the origin? How do they go from the origin to this point here? So in the XY system, you say, oh, go right 4 units, go up 4 units. So go right 5 units, go up 4 units. And so that's going to be like 5x hat plus 4y hat. So x hat, y hat are like the unit vectors. You could also define a pole. You could also define a pole, say that this is the pole where like r is equal to 0. And you say that, okay, rotate this degree. So rotate this amount of angle and then go forwards 5 units. So that's also another way that you can describe this. Just r theta. So infinitesimal thinking is really useful here because um how like infinitesimal thinking is useful here because like of two things. Um one thing is you could talk about dx and dy really quickly. Dx and dy are really easy. So because if you know dx and dy, you can find dx dt, dy dt. So you can just like straight away get velocities. Another reason why infinitesimal thinking is useful is because it tells you how these x hat and y hats go. Like over here, um, in the rectangular case, if you change x and y by a little bit, x hat and y hat are still going to be the same. They're still going to be oriented like in that way. You're not going to change the orientation. Over here, however, in the polar coordinate case on the right, um, you'll see that if you change theta by a little bit, if you change theta by a little bit, right, if you change theta by a little bit, the whole arrow changes. The whole arrow changes in its direction. So as you can see, over here, r hat is here, right? R hat is here, because that's the direction where r is pointing to. That's r hat in red. So theta hat is gonna be the direction where theta points in. So it's gonna be over in this direction. Because over here, theta, and over here, if you draw the tangential parts, so that's theta because of this. So when you change theta by a little bit, the whole coordinate, the whole x hat, y hat changes, the whole r hat, theta hat changes. How does it change by? So suppose let's only look at r hat. Suppose let's only look at r hat. Um, so I'm just showing you guys like how infinitesimals can also be used in tandem with coordinate systems and how like infinitesimal thinking can help you switch between these really easily. So so this angle here. So okay, wait. Oh, okay, yeah. So actually wait, yeah, sure, I'll just use the example. Okay. So one thing to know is that like these two are orthogonal, so these are like 90 degrees to each other. Just keep that in mind. These are 90 degrees to each other. So okay, let's see. I copy this two vectors and zoom them out so you can see them clearly. Just redraw them real quick. So yeah, I'm just like copying these two vectors. This is kind of like sus. Okay, like this. Cool. Okay. So as you can see, this is the original one in the bottom, and the one afterwards is on the top. Right. So what happened to them? So there is a change. There's a change. There's a dr hat. The r hat changed for a little bit. And what causes that change? That change was caused by this d theta. So this d theta causes a change in dr hat. So by how much? So this r hat and theta, so this dr hat is caused by a change in the orientation. And what direction points in the change? The direction that points the change is actually this theta hat, right? Because as you can see, here is 90 degrees. What else is 90 degrees to r hat? Theta hat. So the r hat is theta hat. But is that true? I think I'm missing something here, right? So can someone tell me what I'm missing? Right, so I'm just missing this d theta. So why is there a d theta here? The d theta here is to make sure that both sides have the same infinitesimal size. So what I mean by that is because like if you have d something, it's a really, 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 really small thing. If you have dr hat, it's a really, really, really small change in r. But theta hat is actually something that's quite big. Like, as in, it's just there. It's the size of one. The size is one. It doesn't have like it's not big, it's not small, it's just one. So if you have a really, really small thing on the left hand side and you just have one on the right hand side, you also need to multiply by a really, 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 really small thing called d theta on the right hand side. So that's how you should expect this equation to look like lah. In reality, what you want to write is that this change here is because of the arc length here is because it's the radius times sorry, it's because of um the radius times so the arc length is just radius times the angle. So the radius here is just like one. The radius is one. The angle is d theta. So that's why yeah, it's theta hat d theta. It's because theta hat is like the direction where it's pointing to. So yeah, like that's something that is useful in 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 coordinate systems. The fact that you think in terms of infinitesimals. And as an exercise, I want you guys to think of what the theta hat should be. I will not um actually no, like yeah, I'll just tell you guys that it's gonna be negative r hat d theta, but I'm not gonna tell you guys how you derive it. You should try to derive it yourself. So I'm just gonna leave it question here for now. So if you really want to answer, you can come back to watch this recording. Um, yeah. Okay. I think one last thing is a tour of the math that you need. So I guess okay, I think because like me personally, I think this math techniques part is always the hardest to teach because I don't know how deep I can go and I'm not sure how many examples I can use. So as a parting message, I think I'll give you guys some things. So you don't need too much math. All you like algebra, calculus is can bring you a long way. Oh, the algebra and calculus can bring you a long way already. I mean, of course, algebra is really important because you solve equations and stuff. But calculus brings you one step further. Um, if you know probability, that's also great for experimental stuff, probably in statistics. It's also really good if for stuff like mm, distributions, stuff like like radioactive decay, stuff like um yeah, like error propagation and experimental methods. But like you don't need that. It's like optional. You can get through all of that by not knowing any probability, and you should be fine. Um, but what I would say is that I really recommend you guys like reading out like differential equations because a lot of problems like that, a lot of the Olympiad problems at least, like you could solve them by solving a differential equation. Um, because like you don't have to solve a differential equation. But it's like if you don't get that trick, you can always brute force your way for differential equation. It's a bad thing to say because like it's like it's a bad thing to say because like it's trying to like you might get carried away by like writing down the differential equation, solving it instead of like looking at the actual insights of the problem. But knowing how to solve differential equations is also just a general useful skill because like not all problems are gonna have like cute, pretty little Olympiad tricks. So knowing how to solve them is really important. And lastly, linear algebra is something that I really cannot recommend more because as you can see in today's thing, there's already a lot of references to linear algebra. Like over here, like even though it's something that's really far removed from like vectors and dimensions and vector spaces, even though it's really far removed, you can still see that like the effects are still lingering. Same thing over here. Um, yeah. So I would really highly recommend if you can always start linear algebra early because it's a really useful skill that can bring you all the way from physics to machine learning. It's a really cool thing to learn. Um, but yeah, like you don't need that much math. You like if you know algebra and calculus, that's more than enough for you. Um, I will put some example problems in the handout that I'll send you guys. Um, but yeah, like you don't have to finish them. It's more like your exercise for you. So yeah, I guess that we can call it a night for you guys. So thank you for coming. Thank you for watching if you're from YouTube. But yeah, stick around if you have any questions. See you in the next week. Bye.